The forum is going to begin. It is our honor to have Professor Kenneth Young to give us an introduction on the Shaw Prize 2019. Professor Young, please.
Good afternoon, ladies and gentlemen, and thank you for coming to this public forum organized by the Science Museum in collaboration with the Shaw Prize Council to provide an opportunity for members of the public, that's you, to meet and listen to the Shaw Laureates 2019. The Shaw Prize was established in the year 2002 to promote and foster scientific research worldwide. It is an international award dedicated to honor individuals, regardless of race, nationality, gender, and religious belief, who have achieved significant breakthroughs in academic and scientific research or applications, and whose work has resulted in a positive and profound impact on mankind. Since 2004, the prize has been awarded annually for distinguished and significant inventions and achievements in the following three scientific disciplines: astronomy, life science and medicine, and mathematical sciences. Each prize consists of a medal, a certificate, and a monetary award of $1.2 million. This is the 16th year in which the prize is awarded. The 2019 prizes were awarded 2 days ago with the Chief Executive officiating. We are pleased and grateful that the laureates, in addition to lectures at 3 universities yesterday, are here today for this forum. I shall leave it to the moderators to introduce the laureates. I just want to say at the very outset how impressed I have been by their total dedication over literally decades in working on problems of importance to humanity. Important not only for the tangible impact on our lives and our health, but also important as part of the rigorous and relentless search for truth and understanding that distinguishes us from other species and defines us as humans. While the Shaw Prize celebrates great achievements of the recent past, it is also intended to promote similar, and dare I say, greater efforts in the future. The science of tomorrow belongs to young people, and we are very pleased to see so many future scientists here today. I'm sure you will all be captivated, as I certainly shall be. Thank you.
Thank you, Professor Young. The forum is going to begin with a session on astronomy. It is our honor to have Professor Meng Chung Chu to be our moderator. May I invite Professor Chu, please?
Good afternoon. It's my great honor and pleasure to present to you Professor Edward Stone, Shaw Laureate Astronomy 2019. Let me start by sharing with you a very memorable event in my life. I went to Caltech as an undergraduate student in 1980, 39 years ago. Geez, I'm so old now. Very soon after school started, in early October, the university decided to put many huge TV sets around campus. And they show pictures of Saturn on it. It was a time when the Voyager spacecraft was approaching Saturn. I can still remember today the excitement and the sense of pride and achievement. Everybody on campus. I still remember one day the spacecraft was to fly through Saturn's rings. And we were so nervous and yet very excited to see what's happening. It really left a deep impact on me, myself, and I'm sure it has deep impacts not just on myself, but many people around the world. The Voyager mission not only transformed our knowledge about the giant planets, our own solar system, but perhaps even more importantly, exemplified the human spirits of exploring the unknown, pushing the frontiers of knowledge, going places where nobody has gone before. And today we are so fortunate to have the project scientist, Professor Edward Stone, with us. He's not just the chief scientist of the Voyager mission. He actually led 11 instruments on the spacecrafts. But not only that, Voyager was only one of the 9 missions that Professor Stone was the principal investigator of. He was also the co-investigator of 5 other space missions. Furthermore, Professor Stone served as the director of Jet Propulsion Lab, which is the NASA branch operated by Caltech in charge of most of the unmanned space mission. So during that time, he oversaw very successful missions such as Cassini and the Mars Pathfinder and Sojourner rover and so on. But that's not it. Professor Stone served in many roles for Caltech. He played a key role in developing the WM-Keck Observatory, the pair of 10 meters of telescopes in Hawaii in the 80s. He also oversaw the development of the LIGO Gravitational Observatory. And even now, he is helping Caltech to build the 30-meter telescope. So in short, he's not satisfied with just going to the edge of a solar system. He will take us to the next step to go to the edge of our visible universe. So for all these, I'm truly grateful that Professor Stone is here with us. And I won't read out all the numerous awards he has obtained. I think his achievement speaks louder than all these awards. And finally, I'd like to just say thank to him because he actually wrote a recommendation letter for me when I was a senior student. So finally, let's welcome Professor Stone.
Well, thank you for that wonderful introduction. I've been a very fortunate person in terms of having the opportunity to do many things, and some of which, in fact, are very visible publicly. And you might ask, how did all that happen? I can tell you that when I was the age of the high school students in this room, there was no way that I could have thought about being the chief scientist on a mission to all the planets, because there was space age hadn't happened yet. That didn't happen until high school was 1954. It was 1957 when Russia launched the Sputnik, and suddenly there was a new realm of human activity. You know, we all know about the usual realms. First of all, land, and then the atmosphere and the ocean. Now here's a new realm of human activity, space. The thing which captured my imagination was the idea that this being a new realm meant that there was a lot to be discovered. And because I think some of you know at least that even with the very simple first instruments that the JPL built and was launched in 1958, January, that they discovered the Van Allen radiation belts, where the radiation was trapped in the Earth's magnetic field, bouncing back and forth, creating a hazard which we really didn't know was there, as well as an opportunity for a new kind of science. So so I could not have planned that. There was no way I could have planned, because I didn't know that there was about to be a launch into orbit. And certainly when I went to the University of Chicago to study, I was thinking about studying nuclear physics, because at that time it was certainly a frontier area as well. So I went to the University of Chicago, where Enrico Fermi had been a professor, thinking that's what I wanted to do. But on my way back to the university in the fall of ¡58, I read on the newspapers that, in fact, the Soviets had opened the space age with the Sputnik. And almost instantly, I thought, Now that really would have a lot of opportunities for discovery. The challenge, of course, is to build the instruments that would survive and work in space, get the data back, understand things which nobody has seen before, all of which is what the scientific process is really all about. So I managed to, fortunately I was working with a professor at the University of Chicago who was interested in going from balloon instruments, which go high in the atmosphere but not above it, and to get on rockets to go above the atmosphere so that one can see what's outside the Earth. The cosmic rays were discovered from balloon-borne instruments. These are high-energy particles, very fast, moving nearly the speed of light, which have been accelerated by supernova. And some of them, the fastest ones, can actually get into where Earth is, but most three-quarters of them can't get in. They're held out by this action of the sun. So there was a real opportunity as the capability expanded to move out further and further until we could actually reach interstellar space. I came to Caltech to set up a space physics program at campus. Now, I hadn't considered working at JPL at that time because those were planetary missions, and I'm not a planetary scientist. I'm a physics professor, and you might say, well, how does that work? And it works because, in fact, the instrumentation that's needed for planetary science has many similarities and capabilities that the instruments I worked on to detect the energetic cosmic rays gave me an experience which meant it was possible for me to serve as the chair of the board of principal investigators that was responsible for the science in the mission. And I can tell you it was a wonderful learning experience. But even more than that, it was the fact that in a scientific, many of us in research think things usually move along at some reasonable pace over the year. And you feel good when you learn something and a few things per year. In the case of the space program, we spent 5 years building this Voyager spacecraft, and then another 2 years getting to Jupiter, our first target, none of which resulted in any science. That all happened after we got to Jupiter in 1979. And day by day, every day, there was a flood of new information that was really revolutionizing, transforming our understanding of the solar system and formation and evolution of planets. So it's a very episodic thing, but the returns are enormous when it all works. One thing I did learn, though, and I think it may be more general than just the kinds of things I worked on, that is you need to be optimistic. These programs involve thousands of people. You have to assume that everybody does things right and that no accidents happen along the way or no parts which are fragile finally break, because you can't fix it. So you have to be optimistic that there's a way to do what you're trying to do. But you also have to be patient, because these things don't happen quickly. It took us, as I say, it took about 5 years to convince people to start the construction, another 5 years to actually build the thing, and 2 of them, and launch them. And finally, after all that time, we started getting data that really transformed what we knew and kept us moving further and further out with every encounter, Jupiter, Saturn, Uranus, and then finally Neptune in 1989. That I think one of the things which it comes from this is it's very clear what science, one way to think of science is about finding the frontier of knowledge and finding a tool that allows you to operate on that frontier and make advancements in your understanding. That's certainly very easy to see in this planetary program, because every bit of data you get is new and often will change your ideas. So you need to be patient, but you also have to be persistent. These things don't happen overnight, and often other events over which you have no control, a political process in Washington, for instance, on whether the program should continue or not, or can continue because of costs. So you have to be persistent in realizing these new opportunities. There are really 5 frontiers of space, I think. One is the obvious physical frontier. Going somewhere, sending things to somewhere nothing's been before. It's almost assured to be some discoveries. Sometimes there are a lot of discoveries at the physical frontier. Then there's a science frontier. That is understanding what's out there. And that's often quite different than what we learned from our Terra-centric view of things and thinking. Beyond the science, the scientific frontier is the technology frontier. That is building instruments that function in space and can make the measurements remotely that you can make in the laboratory. So that's another key area of development that is still the case. So we have much more we can design before we really fully are capable to do what you can do in the laboratory in space. Another frontier that I think is an important one in the space and in other areas as well is the opportunity to better life here on Earth. When you think of how many ways the space program has benefited, but certainly the cell phone and the GPS being clear examples of something which affects everybody. But that's an important frontier as well. The final frontier that I think is important is the human frontier. That is the functioning of humans in space. It's clear space is not where humanity evolved, and therefore it does suffer long-term changes. And obviously there's an opportunity from a medical point of view to understand these effects on the human and to see if there's some mitigation that can in fact make things more effective for humans in space. The program, I think, is successful, and they see the space program, when you can look at it and see what you've learned, what advances have you made. You always have to make choices. Those frontiers are enormous. We are clearly not going to visit everywhere. We have to decide where the most important places are. Is it looking for water on Europa mission of Jupiter? Is it looking for water on a moon of Saturn and Enceladus? Because that's a place where here on Earth, wherever there's water, there's life. And certainly one of the key questions, very broad question, is there life elsewhere in the solar system, microbial life? And of course, eventually, is there microbial life in other planetary systems, of which we know there are now many out there waiting for us to develop the technology. The technology frontier there is quite large and difficult. But so that, in fact, one can look at these remote objects and determine whether the conditions in the atmosphere are suggestive that microbial life indeed has evolved there, just as it did on Earth, and create the oxygen which we all breathe today. So that is a sort of a short summary. I don't know. Let's just stop with that kind of a broad overview and take any questions or comments and see how many of them I get right. Thank you.
Thank you very much, Professor Stong, and please take a seat here on the stage. The question and answer session is about to begin. May I also invite Professor Chu to take a seat on the stage and join the discussion.
There you go.
So please feel free to ask questions.
There's one.
Hey, it's a very nice speech. It's inspirational, and I think it's wonderful to send those space probes outer space. As we know, the Voyager goes to the interstellar space. And so my question, I have two questions. The first one is based on your experience and also your thinking, do you believe aliens exist? Considering the super large scale of space and time. The second question is that do you think that it will be a threat to send out those probes to other destinations? Because as I don't know if you have read the sci-fi book Three Body Problem written by Cixin Liu. I think he proposed a theory which called a black forest principle. He assumed we're in a entire universe is zero-sum state, and if other civilization, we have limited resources, they want to survive, they don't want other civilization to survive, and which he also described in his book can be proven in our human history, some civilization was destroyed by other civilizations. So, the two problem is, do you think aliens exist, and also do you think that's a good or bad to send those probes outside?
Well, that's a rather long question. Did you?
Yeah, so the first question is, do you believe there are intelligent lives out there in space? And second question is, would it be a threat to us if we reach out to them?
Okay, I think here on Earth, wherever there's liquid water, there's microbial life. It's going to be nearly boiling, coming into these in the ocean. Can be nearly freezing in the Arctic. It can be in rivers that are acidic, like in Spain. So that means that if you want to look for the possibility of life, you should look for water, where there's water, and try to get the samples of it so that you can look to see if microbial life has evolved. Anywhere here on Earth you find liquid water, you find life. So that certainly suggests that if those similar conditions exist elsewhere, which they almost certainly must, there is a reasonable thought that there would be microbial life. And our challenge is one of showing the signatures of that that would convince people that this is not just more chemistry, but in fact has to do with life. So in terms of more intelligent life or something like that, which is threatening, I think that that's highly unlikely. If you would ask the question in the case of the Earth, 1 million years ago, is there intelligent life on Earth? I think you know what the answer is in terms of any kind of modern capability. It didn't exist. So at the time periods in which it takes a long time to get to the point where there's intelligent life. There were a lot of experiments done by life to get to the human beings we are here today. Can't say it didn't happen somewhere else, but I think it's not very likely.
Okay, what is the ultimate of our universe, you believe? I guess the question is the fate of our universe.
Oh, the fate of our universe. Oh, well, I'm not, maybe you should answer that one.
Well, as far as we know now, the universe will just keep expanding. So it will probably become more boring and more boring. But we don't really understand the dark energy, so we should do more research. Okay.
Hello, Professor. Thank you for your inspirational speech. It's interesting to see many people from nuclear physics go to astronomy. So I got a few questions. So recently I hear there's some research on water in glass state, discussing about how those kind of glass state catalyze the organic forms. So could you comment on this kind of area of research? What do you think what does it mean for organic life form in space? So another thing is that as you are the program manager of all those kind of like space programs, so as a manager, you're going to have many kind of risk analysis and decision making. So could you share your experience on this kind of aspect of things? And also, like, because you deal with many political people, and nowadays it seems to be political scientists are just more bullshitting than actually doing things. So as your experience in dealing with bureaucrats, can you also share experience on that part? 3 questions, thank you.
I'll ask you to...
Yeah, the first question, if I get it correctly, is how do organic life forms form in space? How can they form?
Well, to form, you need to have the elemental composition, you have to have the various kinds of atoms and ions. You need to have an environment which, in fact, causes them to change from one kind of molecule to a more complex molecule. And there are there's a fair amount of research about doing that, not just elsewhere, but trying to understand where life actually began, in some sense, here on Earth, and what the evolutionary path is. And that's an area of active research. So there isn't an answer. It's undoubtedly a result of a very complex process. But it is clear that accidents can have a big effect. It was the dinosaurs, which when the asteroid hit the Earth, the dinosaurs basically were gone. They couldn't survive, and that made the room, the ecological room for mammals to evolve. And so in that sense, an accident really triggered that form change in the nature of the material or the atom of the molecules which are forming. So it's a very complicated story. There's probably not a single answer, but we need to do the research.
Yeah, we need to do research, yes. Okay, let me skip the second one and turn to the more interesting third question first, right? So can you share with us your experience, how you deal with bureaucrats and politicians?
Well, I think that we should give politicians really a strong vote. They continue to support research. They understand that research is a critical element of quality of life and our leadership in the world. And even though they're not expert and they really have to basically rely on the science community to tell them what the most important things to do, they really recognize that it's important for the nation to do this. And it's an area the U.S. has been very successful in leading. That doesn't mean they don't sometimes cut programs. They have to. But I think my experience is that even those without a vested interest really do understand that this is something that's important for the U.S.
Okay. I'm not sure I got the second question correct, but I guess the question is, you had to make a lot of decisions as the project scientists and managing all these big projects. Can you share with us some of your experience, how you make those important decisions?
Well, I think the key is to have colleagues who help you, who are expert, and you can, by interacting with them, form a decision which in fact is more relevant than if just sit in an office by yourself. So I think that's a critical element. One of the things which really I found quite interesting to do during the development phase of the spacecraft, where there are trade-offs of this versus that I had to learn about other instruments in order to be able to make a decision that wouldn't be countered or reacted to. And so it was a real learning experience.
Okay, there's one in the back.
Good afternoon, Professor Stone, and good afternoon to Professor Chu as well. So I have a question regarding the opinion of building telescopes on Aboriginal sacred lands. So in recent years, there has been this sort of controversy amongst Hawaiian people and astronomers because the U.S. government wants to build a telescope on top of one of the Aboriginal so-called sacred mountains. So what are your opinions on building telescopes or so-called taking over Aboriginal land for the purpose of scientific research? And thank you.
Okay, do you want to?
Okay. The question is about astronomers like yourself trying to build bigger and bigger telescopes on sacred mountain. And the Aboriginal people didn't like it. So what's your comments on that?
Well, I think it's clear that I think the reaction when seeing Hawaii is again a reaction having to do with the way the Native Hawaiian community has been treated over the years and not given the respect that they feel they deserve. Some of them want to secede from the U.S. in order to have their own kingdom back. Others recognize that that's probably not practical, but they would like more help with their community. And they see TMT as a way to get worldwide recognition of what they feel are the problems they're facing.
Okay, I got two questions here. The first one is about the Voyager spacecraft. What's the chance of it being captured by aliens in the future? Or will it be hit by celestial objects and destroyed?
Well, okay, the first question was, will it be found by aliens? I think not. I think it's really a message to ourselves that we could actually do this. Think of this. We have launched a little bit of Earth into orbit in the Milky Way galaxy. It will be there for billions of years, long after the Earth. And this is something that we could do. So I think in that sense, this is just a symbol of what we've achieved.
Okay, and then second question is, what advices would you give to young people, most of the audience here, who are interested in astronomy or science?
Well, I think it's I think it's clear that you should look for opportunities to do things. In other words, not just passive interest, but an active interest. Find ways to work on have a summer study, some kind of a summer You can do your own projects, find people to work with who can help you with your project. I grew up building radios and hi-fis and all kinds of electronic instruments, which by today's standards were primitive, but at that time was advanced technology as far as I was concerned. And so I learned a lot, and I continue to learn when I look at whether I should take on a responsibility or not. Often it's important to have enough experience so you can be effective. But on the other hand, if it's nothing new for you, it's probably not going to be all that interesting, and it may not be the best place to be focused. You should try to find things you find interesting.
Yeah, that's one.
Right, so first of all, I'd like to thank Professor Stone for his commitment to astronomy, and I also like to thank the Science Museum for organizing this event today. So the question is, in the course of developing space probes for NASA and the JPL, were there any challenges in development such as equipment failures which were memorable to you? Could you share some details or give some insights on how you overcame those challenges or found a way around those challenges? Thank you.
I did not really get the question myself, but I guess the question is, there must be many challenges for the JPL to manage all these space missions. Can you share some experience, give some examples, how you manage the mission so that you get around these challenges?
Yeah, well, you have to have tests. You have to test at the various levels. When you buy new parts, you have to test the parts to make sure they won't fail just because they weren't made right. And you have to make sure that the critical ones don't fail at all. When you do have failures, you have experts who basically then determine whether there's a way you can test them before so that they don't break after you've selected them. So selection is very important, and they're very expensive as a result because each one is measured carefully to make sure it won't fail in a catastrophic way.
Okay. There are quite a few questions coming. Wow, they are all so long. Okay, let me find the shortest ones first. Is it almost correct to say that there are 100% chance of having life in the huge universe?
Well, it's hard to quantify, but I think it's highly likely. I don't understand why it wouldn't be. I mean, there's nothing that special about the solar system. So I would think that we'll find it. There are lots and lots of galaxies out there which have lots and lots of stars. So it would be a surprise. Doesn't mean it won't happen, but it would be a surprise.
Okay, the next question is about talent development. What interactions or projects for students should a teacher have to develop to nurture the students to become researchers? Could you share some experience on this?
Yeah, well, certainly it has to be something. I think it has to be something which is really up to date. So computers are clearly in that category. I think these robotics competitions, where you're challenged to create a system, not just a motor, but a system of motors which does something with some intelligence. It's that kind of program which is now quite feasible to do as a student, or team of students is even better, because Voyager certainly was a team. It wasn't a bunch of people separately working in their offices not talking to anybody. They were a team, or a set of teams, and I think that's another aspect of learning, is some people that works quite well. Other people, they really want something where they can do it all, and that will in fact focus them on a different set of problems.
Okay, next question. Many people think that space exploration has nothing to do with our daily lives, and it may be a waste of resources. What do you think? What's the benefits of space explorations to human beings?
Well, there are a number of aspects, but clearly one thing is that it's clear that the capability to operate in space often drives the capability we can use here on Earth. The global positioning system is a space system, and yet it's something which all of us use every day. And I think the coding, when you're sending data back from deep space, the signal is very weak. That means it's noisy, and you have to encode the data so that you can recover the lost bits. That's something that's now just standard stuff in your CD player. But it was really first used in space because we had no choice. The signal was very weak. Here on Earth, you can use it to do the same thing from a CD player.
Right. So there are many examples of technological.
Many examples,
yeah. Next question. Space exploration is a field with high risks. Have you ever had doubts about your decisions in this field?
I guess certainly it comes with the business. There's no doubt there is risk. Anytime you see a huge rocket firing, you know that you're in a very risky environment, and it's an environment you can't control. Once you light the rocket, it's going to do whatever it's been programmed to do. So yes, that's part, as I said, you have to be optimistic that there's a way to do it and that you've done the right thing. So you don't have catastrophic failure, at least very often, but you will have failures. I think there's no guarantee in these complex systems there can't be a failure.
Should we have Voyagers 3 or 4? Voyagers N?
That's a good question. You know, you may have, we flew by. We had what's called flyby. That is, we didn't go into orbit. We flew by Jupiter, Saturn, Uranus, and Neptune. We were doing a survey. But following that, we had the Galileo mission, which went into orbit about Jupiter so it could fly by Europa, the moon that we think has an ocean under its icy crust, many times and study it carefully. And so that's the natural evolution of a program to go from flyby, which is the survey of what's out there, and we found a lot of interesting things out there. But when you go back, you want to have more than one chance to look. You want to go into orbit. And that requires you carrying a rocket along big enough to slow down so you get captured, which is another complication which you have to deal with.
Somewhat related question. Dear Professor Stone, if you can build another spacecraft, where do you want to go? And find out about what?
Well, I think I've already said water in my mind is a key. I think there is a mission being developed to go back to Europa, which we, as I said, we know now from Galileo, has a liquid water ocean beneath its icy crust. And we need to look at the entire surface of Europa and look for places where water has come out on the surface that we could capture in some way. And then the challenge will be, what can we learn by instruments there? Or do we really have to think, can we ever bring some of that back and study it with Earth-based instruments? Enceladus is a moon of Saturn. It has water vapor geysers from its cracked surface. And again, the same story applies. It's a satellite of Saturn, so it's in orbit of Saturn. And that, I think, will happen. And I think another interesting satellite is Titan of Saturn, which where the rain is, it has a rain cycle with clouds forming, rain falling, and then lakes forming, except it's not water. It's methane, liquid natural gas, which is going through this cycle. It may have some resemblance to what happened on early Earth before life evolved.
Seems that many people are concerned about aliens and our safety. So the next question is, what will you do in terms of if you receive some signals from unknown sources in outer space? Would it be dangerous to respond to it?
There have been teams thinking of what the protocols are, and I really haven't kept up with that. But there are people who think about this question. I think it's a very remote possibility, actually. But there are now, as you know, looking for life by looking for radio signals coming from various planets, and there are also light signals possibly. So that this whole issue is obviously related to but this is intelligent life, which is even more advanced than I think is likely on most cases.
There's a question there.
Hi, so I do know that the Voyager spacecraft has like these golden records that depict human life, and I just wanted to know that like it's been a while since since the depictions of human life have been put on those records, so if you could change it now to portray us in any other way, how would you do that?
Yeah, you're asking us, today, would you do something differently? Probably so. You have to realize when this was done, it was done in 6 months. It's, I think, really quite remarkable that they managed to look at this wide range of music and pick out a representative sample, not just Bach and Beethoven and so on, but in fact, worldwide music. And I think the same is true for the images they chose to represent life on Earth, and not just human life, but life in general. You could do more, much more. Those were old-fashioned 16 2/3 RPM long-playing records, 12-inch records, which have grooves and a needle. We did provide the needle for someone that would find this, and that can generate pictures. And clearly, today, one would send us a CD document of some sort so that it would be digitized, be much more effective than what was available at that time, and you could have much more, and the problem of what you put on it becomes even more complicated because you have so many choices to make.
There's a question in the back.
Another question about modern day culture and related to sciences. So as we all know, like in recent years, there has been this sort of rise in science-related movies, sci-fi movies, especially in like realms of about space and astronomy and astrophysics and things like that. So what are your opinions on the sciences in those movies? Are they like a way to promote science to like the general people, or they mislead people to believing in fake science facts? Thank you.
Yeah, so the question is, there are many sci-fi movies or science-related movies, such as Interstellar a few years ago. So the question is, what do you think of the scientists in those movies? Are these movies misleading people into what scientists really like?
That's an interesting question. Way to put the question. I think the Interstellar certainly was something which was advised by a very reputable scientist, Kip Thorne. I know him quite well. He's very serious about what he does, but he's also very clear about what is really made up and what is physically possible. And in all science fiction ends up, at least it's interesting, but ends up extrapolating beyond physical reality to try to make a point about what the story is, and I think that and to engage the reader. So I think that's all fine, but you have to. But it's not science fact; it's science fiction.
There's a question on this side.
Yeah, hello. I have a question regarding the type of propulsion. Like recently, we have some developments on the ionic propellant, and I want to know like how do you compare the ionic propellants to the traditional one, like the hydrogen mixed with nitrogens, and will the ionic propeller dominate the space exploration?
Yeah, certainly there are those. One can use thrusters, and that has been done now for some time, certainly several decades. It's the force that you get from that is very feeble, because it's just gas being accelerated by some not too high a voltage. And that gas then pushes the spacecraft gently. It's fine for something where you have lots of time. So that's used, for instance, we want to encounter an asteroid. You approach it, and you can use these thrusters to eventually slow it down just enough so it ends up being in orbit. And so that already happens, and it works quite well. But it can't produce large delta V's. It can't change the spacecraft velocity a large amount because you can't carry enough the ion stuff around to expel. The more you expel, the more you change the spacecraft, but it's speed. But so it's really meant for fine guidance, not so much for big, heavy-duty thrusting.
Okay, there's a question here.
Thank you, Professor Stone and Professor Cho. And I want to know, for such a big project like Voyager, you need to do a lot of preparation, right? And what happened? Something unexpected happened, and that made your project failed. And this is my first question. And the second question is, the communication is the very important part of the project, right? Then when the battery run out, you lose the connection between the Earth and the spacecraft. Is any possibility that we can reconnect again when the battery runs out, such as because we can get some energy like from the solar radiation? So I think I don't know whether is there such a possibility to reconnect it again.
Yeah, the second question first. If I remember correctly, actually the Voyager spacecraft, the battery will run out somewhere in 2020, if I remember correctly. The question is, after the battery is out, is there still any possibility for us to connect to this spacecraft?
Yeah, we need to have, it has to have enough electrical power in order to have a radio to receive our signal and has a transmitter to transmit back to us. And that takes electrical power. When we don't have enough electrical power to run the radio, then we're stuck. That's it. That's the end of the mission in terms of communication. After that, it's what I call our silent ambassadors. They'll be out there, but they won't be talking. They won't be telling us anything.
Do you always prepare a plan B in case something didn't work out?
Depends on what it is that's the problem, but I think redundancy, we often on Voyager, we had 2 almost of every critical subsystem, so if the primary failed, we could turn on the second, and we've done that in a number of cases on Voyager, and we're running on our second instrument. So that's one thing, is you build in the capability to do other things. Sometimes you just reprogram what you've got to make up for it. It may not be quite as good, but it provides some connection.
Okay, another interesting question here. So many space projects are adapted to make weapons or for military use. What do you think about using astronomy for military purposes?
I guess I'm not sure what.
Maybe some space weapon, I guess that's in mind.
Well, I don't. That space weapons are not something I really am an expert on. So.
Right. Yeah. Do you believe the universe is infinite?
Do I believe the universe is infinite? Well, it's expanding, but the question is how it will cool off, as you mentioned. But is the universe infinite?
I think so.
Yeah.
I think so. It's not a matter of belief, right? We have to do research to find out. Okay, next question. What's your view and opinion on interdisciplinary learning? So, for example, should a scientist be a master in politics as well?
Well, I don't know that you've got to be a master of everything, but you do need to understand a lot. If you have a complex system, and by that also includes the system of support, the Congress, the people who decide whether you get money or not are part of that system, if you like. So you do need to be aware as to how the various aspects of getting into space are motivated and managed by different communities and who may not exactly deal with problems in the same way. So your job as the leader is to figure out how to make this thing work.
Actually, I'd like to change this question, but the original question is, do you think that unpiloted spaceships should be launched to explore planets far from the Earth? So like the Mars rover and unpiloted.
Well, yes, certainly those are the things we have been doing. We haven't sent a human being to Mars yet, and it's some time off before that will happen. But there continues to be an interest in human spaceflight as part of that frontier.
Okay, let's take some more questions from the floor.
Hi, I have a question about space debris. So I heard that every single time when we send something into space, that a lot of debris will end up in Earth's orbit, and it accumulates, which then eventually could possibly create a barrier around the Earth that makes sending new things into space really hard or even impossible. So my question is there any way, is there like a solution or something that we're going to be doing to possibly lower the space debris so there would be more future missions? Thank you.
I'm not an expert in that area. I know it's generally a problem. One of the things that has long been done is that the spacecraft design are supposed to prevent the breakup of particles. If they have, not a breakup, but if you have say a bolt which is supposed to sort of break so something can separate, that you don't want the bits and pieces of that bolt that broke up to be left in orbit. You want to capture them. So there's some active protection which is built in, but there can be a collision. In fact, there was a few years ago. Two spacecraft clipped each other, and of course, well, the space is getting full, and then there's debris. So there's a lot of concern about that problem in near-Earth orbit. This doesn't affect where Voyager is or anything that's beyond the atmosphere of the Earth, but it does affect things in Earth orbit where once they break up, they become subject to just running into the very faint atmosphere up above and slowing down and burning up in the atmosphere. And the process may, in fact, generate more problems. So yes, that's a problem. And there are groups looking at there's a way to mitigate it.
Okay, thank you. Unfortunately, our time is up. So let's thank Professor Stone again.
Thank you very much. Please take a seat on the floor. Now, we come to the session on mathematical sciences. It is our honor to have Professor Pak Chung Cheng to be our moderator. May I invite Professor Cheng, please?
Distinguished Shaw Laureates, honorable guests, fellow students, ladies and gentlemen, good afternoon. Since there are many students in the audience today, let me just do a quick survey. How many of you like mathematics and find it interesting and useful? Please raise your hands. That's not bad. Well, Professor Young obviously raised his hand. Well, mathematics is usually considered by many students and people, actually including me, to be a difficult subject, very abstract and hard to understand. Whilst most mathematicians are gifted talents, genius, but they are usually not that easy to communicate with, and probably sometimes even boring. However, it is widely recognized that mathematics is an autonomous intellectual discipline, and it plays a fundamental role in modern science and technology, creating profound impacts to human mankind. And that is why one of the 3 annual Shaw Prizes is awarded to individuals who has made outstanding contributions in mathematical sciences. And if you have the opportunity of talking to this year's Shaw Laureates in mathematical science, and I encourage you to stay a little bit behind and talk to the laureate this year, you will find that his humorous and lively character and style will prove the usual perception of mathematics wrong. Dr. Michel Tarragand is the 2019 Shaw Laureate in Mathematical Sciences. He was born in France in 1952, and he overcame a severe vision problem in his early childhood to focus study and build up a solid foundation in mathematics. He got his PhD in 1977 from the University of Paris 6. And since 1985, he has been Director of Research at the French National Center of Scientific Research, that is the famous CNRS. He works in the areas of probability and high-dimensional geometry, 2 seemingly different areas, and has made significant contributions in his study of suprema of stochastic processes, concentration of measure, and spin glasses. I don't quite know spin glasses myself, but definitely it's nothing to do with glass. Well, Dr. Tarragand is highly praised for his patience, persistence, and perseverance in tackling difficult mathematical problems single-handedly. He has written monumental and influential textbooks on all the above 3 topics, and they are now central to the work of many other mathematicians. We are privileged to have Dr. Tara here in the auditorium today. And he will share with us his findings and passions in mathematics, and also the ups and downs in his journey to becoming a great mathematician. Without further ado, please join me to welcome Dr. Tara.
So, to make the question and answers smoother, I have thought in advance to some question you are most likely to ask about mathematics, and I will explain my answer, and then of course there will be more questions later. So the first problem is what does mathematics study? And the main problem with mathematics is that mathematics studies abstract objects and structures. And just to understand the object we study, it takes basically doing a PhD to understand these objects in one single area. As a corollary, my advice is never attend a mathematical lecture unless you already know the topic, because after 5 seconds you will have no idea what the person is talking about. This is very sad, but that's the way it is. When I myself started, I attended the seminar of Professor Choquet, and I can tell you I didn't understand a single talk for the first 2 years, because I didn't know what the object they are talking about. So you have to hang on, study the object, understand them, and after that it becomes much easier. Now, what are these objects? You see, what is the nature of the object mathematics studies? On one hand, you can say that these objects exist only in the mind of mathematicians. Now, fortunately, mathematicians agree about these objects which exist on their mind. But do they exist only in the mind of mathematicians? Now, that's a philosophical question. And it's a very interesting one because people thought about that question a very long time ago. In the West, the first person who thought about that is the philosopher Plato, who died 347 BC. And that was at a time where the Greeks knew significant mathematics, like they knew the Pythagorean theorem, for example. And Plato had this extraordinary idea. He thought that the mathematical ideas have a life of their own. They exist independently of physical reality. It's a very interesting thing to think about. In the same line, you can ask a question, do mathematicians discover theorem? In the sense that the theorem was already there. It's just that we had not discovered it, the way like we discover a new law of nature. Or do mathematicians invent theorem in the way that the theorem did not exist before the first person proved it? And it's like a way you invent a technical device, a new electronic device which had never been made before. That's again a very interesting philosophical question. But in fact, in practice, when you are a mathematician, you really end up in believing that these objects you study have an existence of their own. Otherwise, you just couldn't spend all your life studying them. So for the practical point of view, the answer is that for a mathematician, these objects have a concrete existence. What are the main tools of a mathematician? Now, the answer to that is absolutely clear. That's the main tool for a mathematician. Now, after doing research for 10 years and filling about 47 different files to get more funding, I could get another important tool for my research. and which I have used a lot, because actually, you know, when the pencil doesn't work to prove your theorem, you can really revenge on it very efficiently. Now, this was a long time ago, of course, so now the situation is a little bit different, is you do have other things you use. Now, in particular, of course, you use internet to communicate with your colleagues, you know. When I started to do research, I was collaborating with a British mathematician, and from Paris to his city, the letters took 10 days. You know, now you can exchange 5 mails a day. This is a different game. Now also the task of writing up your mathematics. Now used to do that with an IBM machine with ball which has to be changed. It was excruciating. Now you have computers who do that extremely well. And there are also areas of mathematics, not my areas, but areas of mathematics where you can sort of experiment. If you conjecture some kind of behavior, you can make computation in concrete cases, and it helps you to discover the answers. Now, what's the importance of mathematics? The importance is completely unexpected, because there seems to be, at a very deep level, there is a relationship between mathematics and the physical world. And in fact, in the West, the first person who really expressed that is Galileo. And Galileo explicitly wrote that the law of the world was written in the language of mathematics, and that was around 1600. He expressed that. And of course, it's still true. The way the famous physicist Eugene Wigner put it, that he spoke of the unreasonable effectiveness of mathematics. Mathematics are very effective in describing the world, but that's unreasonable. Why should it be the case? This is a great gift to mankind, because we became pretty good at mathematics, and so it helped us becoming pretty good at studying the world. Though the way Wigner put it is, we don't understand this gift, and in fact we don't deserve it. Why are things that way? You know, the universe could be incomprehensible to us, but it's not. So one simple example is what everybody learned in high school, imaginary numbers. Now, imaginary numbers were invented maybe around 1600 to solve some algebraic equations. And the reason they were called imaginary numbers is that the most important imaginary number is a number I, whose square is -1. But when you multiply a number by itself, you get +1. You get something positive. So a number whose square is -1 cannot exist. It has to be imaginary. That's the way this was perceived at the beginning. Now, later on, people understood that no, these numbers are not imaginary, so we changed the name. Now we call them complex numbers. And it turned out that these complex numbers are essential in the understanding of the universe at a very basic level, for the simple reason that the entire theory of quantum mechanics relies on complex numbers. So, another way mathematics are relevant is through the use of models. Now, what's a model? Now, universe is very, very, very complicated. So one way to study it is we build small replicas of a small part of the universe. So a mathematical model really is a set of rules. And it's an object which is described precisely enough that you can basically compute everything about it. But the art of making a model is your model has to be simple enough that you can really understand it, but on the other hand, it has to be complex enough to reflect reality. And this is very difficult to exactly decide what goes into the model. But once you have figured that out, this becomes a very powerful tool. And there are so many areas now which mathematical models are completely essential. Now, people love to ask the question, are the mathematics to which you contributed tell me what's the practical use of that. Now, I absolutely hate this question because, I hate it for a philosophical reason because, for example, I'm personally very much interested in astrophysics and astronomy because they help me to understand better my place in the universe. And I think that's very important for me as a human being to understand that, even though I cannot say there is any practical application for many of the astrophysics discovery. But I can give you a sort of general answer about the mathematics to which I contributed, not escaping the question. So nonsensical question, but let me tell you, I cannot be certain that they will not be used. Okay? At least indirectly. In which way? Things in science, everything is interconnected, you know. One area which has obvious immediate impact on our lives is statistics. We need statistics to decide which are the medical treatments which are effective. We need statistics to decide which are the requests made in Google which will lead to some marketing plan we need for all kinds of purposes. And to design statistics, you don't design statistical tests by chance. You design statistical tests because you get a sort of global understanding of what is happening. And the design of statistical tests on a model is based on the theory of probability. And one of the things on which I worked really helps to understand some general feature, some universally true phenomenon in certain model of probability. And knowing this, I know I've talked to some statisticians and it actually helps them to design models. So indirectly, what I have done will somewhat contribute, even though you cannot really pinpoint it very precisely. Now, and a completely different question. When you are a mathematician, how do you choose on which problem to work? Now, this is the most difficult question you face as a mathematician. It's so easy to go wrong. It's so easy to go wrong because you can go wrong plenty of different ways. It doesn't pay to choose problems which are too hard. You know, everybody wants to solve the most famous problem of mathematics, which is the Riemann hypothesis. Okay, I won't try to solve it. I know I won't solve it. Other people have tried. If you try a problem which is too easy, well, sure, you will solve it. You may even publish a paper now. Everything you write can be published, but it won't bring anything to anybody. So you have to find a problem of the right difficulty for your own ability. Sort of the hardest problem you have a chance to solve. And of course, this is very difficult because before you solve the problem, you don't know how hard it will be. That's a difficulty. Also, beside the fact of choosing the level of difficulty of the problem, of course, there is even harder is which area should you work. Now, it's clear, when you develop something which is called mathematical taste, and after a while it becomes clear that one can ask plenty of questions in mathematics, and it's clear that many of them are not interesting. They are too specific. Okay, you answer that specific question in that little corner, and so what? So it's sort of not so difficult to figure out problems you shouldn't study, but there are still plenty left. And another difficulty is that it doesn't always work to make a frontal attack because, if something is a problem, it means other people have tried before you and they couldn't solve it. So the way they attack the problem was not the good one. You have to find another angle. And sometimes, or it happened several times to me, that I've been led to find the correct angle on an important problem. Because before that, I had studied a problem which I knew was unimportant, but I felt I had something to learn by studying that unimportant problem for the very simple reason that it was natural and I couldn't solve it. So I studied it, I could solve it, and he gave me an idea which I could use to solve an important problem. So life is hard. There is no simple, easy recipe to decide what you should study. Very often, great advances in mathematics are made by bringing in a new point of view. Okay, that's good again, but how do you do that? Now, I was very lucky because I studied probability without having been raised as a probabilist. I learned analysis, mathematical analysis first, and I gradually shifted to probability. And when I came to study probability problems, then I had a point of view which was not the same as the people who had started studying probability, and it gave me ideas to consider things that probabilists would never have thought about. So that's a kind of piece of luck to do that. Another thing is you have to be persistent and determined. My method to solve a couple of good problems is that I really literally worked on hundreds of different problems. And you don't succeed all the time to do something important. Also, now that's maybe a piece of advice which is not easy, that was my own taste. I concentrated on structure which I felt were important, which were not the things which were fashionable, you know. In mathematics, you have new areas open, and then people rush in, and it becomes very fashionable, and you probably. But I resisted that temptation. You know, I was fascinated by some simple objects, and I spent a long time thinking about them, and I couldn't understand why other people didn't find they were important, but eventually they turned out to be important. How does one solve mathematical problem? First, you need to understand the basics very well. You need to master the basic technique. Now, that's not true only in mathematics. It's true in anything. You know, if you want to be a concert pianist, you will practice 10 hours a day. Okay. The way I started my mathematical life, when I was in high school, I solved every single problem in the textbook. When I went to university, I solved every single problem in the main textbook. No miracle. Now, once you really understand well the basic structure, well, a problem, you have to find a way not to get stuck. So one way is you have a difficult problem. Well, try to find a simpler problem which sort of resembles the one you cannot solve, but which somehow you believe has the same kind of difficulty. I would call that a toy situation. You try to study toy situations. And other advice is work until exhaustion, but not more. Now, it's not a joke, you know. I'm now in contact with a very good Chinese student who believes that the way to succeed is to work 14 hours a day. You know, that's not true. You should not work continuously on a problem too long because your mind gets stuck. So you start running into a circle and you don't make progress anymore. So there is some work which is done inside your mind and which you cannot control, and your brain needs time for that. So one strategy you can use is you try to prove the theorem, and then you try to prove that the theorem is wrong, because it gives you a different point of view. That was very successful for me. So you alternate because trying to prove the theorem is true and trying to prove that it is wrong. Now, Okay, I'm sorry, I will take several more minutes because this is the interesting part. So, in truth, now, the interesting part is how does it work in the mind of the mathematician? And the truth is, of course, nobody understands how the mind works. The idea, they just form into your head. You know, you stare at something, and then suddenly you notice that there are two pieces which fit together. And now you see it and you didn't see it before. This is sort of an instant jump in your understanding. But don't expect that this will happen every 5 minutes. You have to be very determined and very patient. I spend half of my life staring at a blank piece of paper, trying to notice something and make some kind of progress on the problems I was studying, you know, making little doodle and hoping that ideas would come, and at some point they come. Now, if you are reasonably good at it, being a mathematician is the best job on earth, because you get paid to do what you enjoy the most, and that's very difficult to achieve. This. Now, the problem that when I say reasonably, idea comes to your mind, or they don't. And I had very good periods where I had several good ideas a year, and then I had one good idea a year, and then I had one good idea every 2 years, and then there was a lull, and then I had the last good idea, and then I never had any more good idea anymore. And I tried to whip my own back as hard as I could, and it didn't do any good. So when the ideas stopped coming, that's it. What advice I could give to a young mathematician? So I keep repeating the advice of my advisor, Gustav Schokke, because it turned out that this advice was exactly what I needed for my personal career. And so I'm hoping that there will be somebody else here to whom this advice will be useful. When you are given a mathematical problem, there is often a lot of structure. And the trick is you remove all the part of the structure, as much of the structure as you can, so that still the problem makes sense. Then it makes very much easier to focus on what's the heart of the matter. So, I mean, you have to not to use some of the data, you know, which you could be tempted to use, but in fact, it's an obstacle. So I hope this advice will serve you as well as it served me. We'll stop there. Thank you so much.
Thank you very much, Dr. Talakon, and please take a seat here on the stage. The question and answer session is about to begin. May I also invite Professor Cheng to be seated on the stage too?
Thank you. Well, this now comes to the question and answer sections. But please bear in mind that mathematicians nice, precise and concise argument. So if you have any questions to raise, please put it in the neat way. Probably not more than 2 or 3 lines, so that I can understand and translate it to Dr. Talagram. Okay? I can hardly see the audience. Any first questions from the floor? Yes, please.
Could you explain for any layman in the audience what exactly your work was about? Like, what did you manage to achieve?
How many time do you want to stay behind? How much time? Please.
You know, you notice the first line I wrote in my transparency is that the main problem with mathematics is that it deals with objects of which we do not have an immediate perception. And the objects on which I prove theorems, it took me about my PhD just to understand really what they were. So the task of explaining to the layman what the theorem could be is basically impossible. Now, no, it is impossible. So I have given, I will repeat sort of the best answer. Okay, I'll elaborate a little bit on the answer I gave. When you it's about model. So I studied probability theory. So probability theory makes a model to predict phenomenon where chance is involved. So the example I usually use is the roulette, because that's many people bet a lot of money on that. So when you play the roulette, you bet whether the outcome will be black or red. If you make the correct prediction, you double your money, otherwise you lose it. Now, people who gamble in the casinos, I understood they record the outcome of the roulette for a long period, and they try some complicated manipulation in order to predict what will be the next outcome. For example, if you ask it happens once in a while that red comes out 10 times in a row. Now, if you ask a typical gambler, he will tell you, no, now, black is heavily favored because it cannot happen that you have 11 times red in a row. Now, the mathematician built models which don't work that way. They will model where these events are independent. Now, of course, there is a technical definition of independent, but in practice, it means that the outcome now I will have of the roulette is not influenced in any way by any of the previous outcomes and will not influence in any way the future outcomes. So this idea of independence is really foundational in probability. And my piece of work, which I like the most, deals with concentration inequalities. You can describe it at a very high level, that it describes new properties of independent sets. And since independent sets come everywhere in probability, this type of phenomenon really comes in a lot of situations. That's why they are useful. So that's basically the best answer I could figure out at that level. Thank you.
Thank you. Okay, this is simple enough questions, but why do you love mathematics?
I usually answer that by a joke, but all the jokes have an element of truth. I did mathematics because I was so bad at everything else. But it's not half. I love physics too, but when I had to choose between mathematics and physics, there were no jobs in physics. So I decided for mathematics. That's perfectly sensible way to do.
Yep, wonderful.
I would do the same now.
I have another easy question for you. He's asking, what will you do when you do not have ideas to solve the mathematical problems?
Well,
I understand that you jog a lot, you run marathon. Is there anything to do with that?
No. What will I do? Okay, actually, the last time I had a good idea, an idea I liked, was 2005. And as I said, I whipped my back after that, and it didn't do any good. But you still can do, there is a lot of things, of course, useful things you can do. In a lifetime of working very hard, you learn a lot of things. You learn a lot of technical things, which are, as I said, technical things. The way how to put the epsilon delta together to make the proof work. That's fundamental in mathematics. And then I wrote textbooks to explain this, everything I knew. So write the theorem I had proved in great detail and with the best possible explanation. And actually I was rewarded because when I wrote one of these textbooks, I solved the problem I had been working on 30 years, but I wouldn't call the solution a great idea. It was just under my nose for the last 10 years and I had not seen it.
Okay, well, I have 3 questions from the gentleman, I suppose, I don't know. But let me just put it this way. Okay, he's asking, Dr. Taragram, do you believe that mathematics is the language of the universe? Or is it actually just a tool to allow us to understand the universe in a beautiful manner?
Believe. Do I believe? I'm a scientist. I try not to believe too many things. It's a fact. It's a fact that mathematics as I say, Galileo discovered that, and it's a mystery. It's really a mystery. It seems that mathematics has a lot to do with the language of the universe. It seems it's a fact. But we don't. What do we know? You know, for example, we don't understand the way the human brain works. If I understand correctly the status of that, and will mathematics help or not to understand that? I don't know. Maybe not at all. So
do you think there might be a completely new discipline, probably different from mathematics, that can successfully better describe the universe? Is that possible? Is there such a discipline that you think might be emerged?
Different from mathematics, it's difficult. New mathematics, the physicists actually, it's a great time to do mathematics now because mathematics develop new direction on itself, but the most important things which happen in mathematics is when there is influence from another domain. You know, there has been an influence from physics a very long time, and recently the string theory had an enormous impact in mathematics, essentially because physicists really invented some new mathematical structures, and another impact is going to come from computer science. It's obvious that there are millions of artificial intelligence, there are millions of problems which mathematics will have something to say, I'm absolutely certain, but it will take a huge amount of work before this is being done, and there is an infinite areas of possibility of that I'm certain of that. Yes.
Okay. Question from the floor? Anyone would like to speak up? Yes, that's one.
Hello, Professor. So nowadays, big data has become a thing, and then opinions and information is become very important in statistical physics, in statistical research field. But then also applying those kind of statistical principles into like different kind of fields in such as political science and become more like divisive society. So what do you think about like this kind of statistical field trying to find trends, but at the same time like creating different kind of division in society? What do you think about this kind of problems and dynamics?
You will have to repeat the question. I didn't understand it.
Can you repeat the question? Probably make it a little bit short. You know,
a little bit short. Okay. Yeah. So basically, statistics is about processing information and finding trends. But at the same time that nowadays people are finding trends of what they want, not really about the trends. So what do you think about this kind of dilemma today that people are not looking for actual trends, but what they want to see?
No, I mentioned these general facts about statistics, but I'm not a statistician myself, so I cannot really give a competent answer to that. Of course, but you can see statistic helps. You know, in statistic help you. How do you decide? How do you decide if a medical? You know, if you have a medical treatment which has some very negative side effect, how do you decide whether you should recommend it to your population or not? You have to make an analysis whether the benefits are better than the side effects. And that's only statistics is the only tool we have for that.
Okay, I have a couple of very interesting questions here. First one, if you were not allowed to study mathematics, what would you choose to devote your time to?
Physics.
Okay. All right, okay, that's great, wonderful. All right then.
Okay, let me. Okay. That's what I did actually. I love physics, and I was so sad I couldn't study it because I had to, make a living and study mathematics. So when I reached 60, I started learning physics for my own enjoyment, and I ended up by spending the last 6 years of my life writing a book about physics, the book in which I would have loved to learn what I couldn't learn in the existing textbooks. So true to my word.
That's a cheating answer, actually. But anyway, let me move on. This one is also interesting. The question is like this. For laymen, what are the basic tools other than add, subtract, multiply, and divide we should learn to best apply in our daily life? Do we need square root? Do we need sine, cosine, and all these other things?
I will tell you, to learn how to get an order of magnitude. You see, when I learned that when Google interviews people, they try to guess the best mind, and they will ask you how many ping pong ball in your head. Tell me how many ping pong balls fit into a school bus. That's an excellent question. If you can come up with an appropriate answer within a factor 10, this helps you much better to understand so many things in your life. That's what I would say.
Very good. Now I have a question raised by a professor from Hong Kong UST. Professor Wang, are you here? Where is Professor Wang? Oh, okay. So why don't you, is that you who raised the question or is Professor Wang? Okay, would you like to speak up for these questions? Or you want me to? Okay, anyway. Professor Wang from Hong Kong UST raised the following question to Dr. Taragram. He said, do you have any good experience, suggestions on how to introduce abstract mathematics, for example, high-dimensional space, to the public?
I have been, lucky or unlucky, depends, to have a research position on my life, so I have no experience in teaching. And being a competent, I'm not fool enough to believe that being a competent researcher makes me competent about deciding these questions. So I don't know. Because I have not tried to.
You have not tried.
I have not tried to.
Would you like to
teach
spend
people
some
that?
time?
So I don't know what's the best way to do.
I see. Would you like to spend some time figure out some new ideas while you jog? Okay, right. Now, this is another question about. Well, you did mention that don't work until exhausted.
Work until exhaustion, but not more. That was the
work until exhausted, but don't work on a problem for too long, right?
Yes.
That's right. Okay. How to keep this balance between two things?
How? Again, we know people are all different. There are all kinds of minds who do mathematics. Don't think all the mathematicians work the same way. So I'm talking only from my own personal experience. When you have not made any progress for a couple of weeks, maybe it's time to do something else. That's what I would say. I explain, and you have these jumps when you fit two things together. If nothing moved for 3 weeks, try to do something else. And you go back. I've always taken several months not doing any mathematics at all every year. And very often when I come back to mathematics, it's when I have good ideas. And this is known phenomenon. I read this very little nice book by Hardy, where now Hardy was living in 1930 in England, so he didn't travel much, but he didn't work on weekends. And he explained that the ideas were coming on Mondays. So that's a very deep principle,
right. Okay, I have on my hand this question asks you, which number or formula you would use to describe the beauty or characteristics of mathematics?
No, I don't know. I don't. I don't know. I apologize. As I explained, I worked on many problems, but I know only an infinitely small proportion of mathematics, so it's difficult for me to answer this question. People we think the prime number theorem. There are some very famous. Euler's formula, Euler's formula.
Euler's formula.
Euler's formula, yeah. E to the I pi.
So it's probably depending on what particular subject area within mathematics, right?
I'm sorry.
Is that what you're referring to? If we have to pick what formula,
also, there are also different. There are probably different answers to that question, depending the level of difficulty you choose. For
Absolutely,
that.
Understand. Right. Questions from the floor? Would someone want to speak up, or then just no? Okay, then let me read it out. The question is like this. Are mathematical entities, like numbers, 1, 2, 3, and so on, right? Objects existing even without human beings, or they are merely created by human minds?
Now here, I will quote Paul Erdős, who was a great number theorist, universal mathematician of the 20th century, and he was talking of the prime number theorem, and what he said the following. He said the prime number theorem existed before mankind and will exist after the last human being is dead. That was his feeling about that. This is somehow you can believe that the natural numbers have an intrinsic existence. But again, this is a philosophical question.
That's right, yes, absolutely. These questions try to challenge you and ask, will you try to prove Riemann hypothesis?
Well, I already answered it. There is a story about that. The famous mathematician Paul Cohen, who solved the continuum hypothesis. Now, after that, he tried to solve the Riemann hypothesis, and he didn't prove anything the rest of his life. It's clear that a frontal attack is not going to work. One has to set reasonable goals and iterate. The way I put it, how do you walk from Paris to Vladivostok? Well, you start by taking one step in the direction of the east.
Okay, are you satisfied with the question? Who raised this? Anyway, well, I did mention that I don't understand at all about spin glass theory. Okay, but here is the question, structured in this way. He said, the spin glass theory has been applied in information processing and associated memory, right? And do you think this theory will be applicable in machine learning as well?
Unfortunately, I have not worked on spin glass for now 15 years, and I really cannot answer that question. And also, there is some confusion because the word spin glasses, that same word, are used to describe many different objects. And the spin glass on which I work are mean field model. They are really part of mathematics. And the reason I worked on that is they are mathematics which were done by physicists' method, which I found was not tolerable.
Okay, right. Here is the question which I like. Well, I'm sure you all agree with me that, it's not difficult for us to interest our students on computer science, right? Whether, they spend a lot of time on computer anyway, internet, mobile phone, and so on. But on the other hand, on talent development, what advice you would give to educator, teacher, and also students on nurturing future researchers, masters in mathematics? How can we do that? How can we interest the student nowadays and get them to be inspired to become great mathematicians?
Well, I'm sure all the great professors here will come with answers to that.
Well, I teach engineering, electronic engineering. I always have difficulty in convincing my students that mathematics is important, actually. Would you give me some advice? How can I do it? How can I be successful in stimulating them?
Now, as I explained, I had very little contact with students, so I really cannot afford any advice.
How about your graduate students? Do you supervise graduate students?
No, I don't.
Oh, okay,
no.
right. So you really work single-handedly?
Yeah, I really work single-handedly.
Okay, great.
Yes. exactly the opposite of somebody like Professor Stone, who had a very large team. Then I'm a one-person team.
Okay. This is another interesting question. I never thought about this before. He asked you, Dr. Taragram, do you think learning French and philosophy help people study mathematics?
I'm sorry, I don't understand the question.
Well, the question is, do you think learning French as a language, and philosophy as a different subjects, that will help people study mathematics?
Well, I learned French and it helped me to do mathematics.
Are you also a philosopher?
No, you see, there is no final answer in philosophy, and there is no definite argument, and I'm absolutely not at ease in philosophical discussions. This doesn't appeal to me at all, because you can endlessly talk and you never reach a definite conclusion. It's a different area.
Okay, there is actually one follow-up.
But I believe that bilingualism is important.
It's important.
I try to make my children bilingual, and they try themselves to make their children trilingual.
I guess at some time people speculate that for those who are good in language should also be good in mathematics. Is that right? That's about the brain development.
I learned also that being left-handed is correlated with being a mathematician. I'm left-handed. And being allergic is correlated to be a mathematician.
Really? Okay, right. I have a follow-up question from this guy, and he's asking. He's asking, would you give any advice for any individual who would like to do self-learning in mathematics? Really want to become a mathematician, but without going to school, or do it by himself through self-learning, internet, and all these things? Would it be possible?
It is very difficult. I experience how difficult it is to do self-learning, because, as I said, I tried to learn some physics when I was 60, and I didn't have anybody to help me, and it was self-learning, and either I really lost too many neurons, or the textbooks are not optimal, because they are not designed for self-learning. So self-learning mathematics, you would need to ask good advice about which books to read, because some books are absolute killers, in the sense that the author throws a lot of abstraction at you and you have no chance to read them. This is a very difficult issue.
Okay, right. Time is running up, as we still have a few minutes. Let me put the question in this way. He's asking, you just told us that you work single-handedly, but on the other hand, do you think mathematicians can actually work closely with scientists who are not good in mathematics and then come up with something fruitful? Is that possible?
Well, experience will prove if that's possible. I have not done it myself, and I wish I had done it. It would have been a great experience.
Okay, are there any more questions from the floor? That's one at the back.
Good afternoon, Dr. Talleyrand, and to Professor Cheng as well. So I'd like to ask a question on nowadays teenagers' view to mathematics itself. So a lot of teenagers find mathematics really boring, and if you had the chance, how would you change that?
Well, of course you find mathematics boring because they are forced on you. You see, that's the thing. You are forced to take these mathematical courses, and but once you get into it, this becomes extremely exciting. It's once you become competent at something, it's no longer boring. Probably students who start the piano and have to learn, to do scales and scale and scale, they find that very boring. And once they master that, they love it. This cannot be avoided for any difficult topic.
Do you like the answer? Good. Any more questions? There's one there. Okay.
After hearing that you're saying that you're a one-man person research team, why do you do that? Why do you do teamwork?
When I say work all by myself, communication is very important. I learned a lot by going to conferences and talking to people, and these people gave good problems to me. That's really the way it worked. But the way mathematics still is an individual game, because the thing is you have to have the right idea. It pops into your head now, and there are some people who do great job in collaboration. I know there are plenty of examples who do great job. It just happened that maybe I never found the right person with whom I could collaborate. It's just happened to be that way. I wish. I'm sure it's much easier when you find somebody with a different point of view and about your same level of ability. It must be much easier to progress because each of them sees the angle the other doesn't see. I was just not lucky to find the right persons. And also, I had this taste for problems that other people didn't consider important, and they wouldn't want to work on them.
Okay, I think we have already exhausted our time. And perhaps please join me to thank Dr. Taragram again. Thank you.
Thank you so much.
Thank you very much. Please take your seats on the floor. The last session of the forum is on life science and medicine. It is our honor to have Professor Y.E. Chen to be our moderator. Professor Chen, please.
Well, the next topic that you're going to hear about is not as abstract as what you just heard, and it's easier to earn a living, according to Dr. Taragram, than physics. So, our next speaker is the Saul Prize in Life Science and Medicine 2019 laureate, Professor Maria Jason. Professor Jason was awarded the prize for her groundbreaking work in the creation of double-strand bricks in the mouse genome and studying its repair mechanism. She saw that localized double-strand bricks in DNA stimulate recombination in mammalian cells. Her understanding of DNA repair mechanisms, in particular homologous recombination, is essential for and led directly to the development of tools that enable us to edit genes at specific sites in mammalian genome, a process called genome editing. This facilitates the creation of subtle genetic alterations at targeted loci in the genome, an approach essential for gene therapy and correction of defects in disease caused by gene mutations. Professor Jason is an investigator at Memorial Sloan Kettering Cancer Center and professor at the Weill Cornell Graduate School of Medical Sciences, New York. She obtained a PhD from Massachusetts Institute of Technology and was a postdoctoral researcher at the University of Zurich, Switzerland, and Stanford University in the USA, prior to joining the faculty at the Memorial Sloan Kettering Cancer Center. Professor Jason's research accomplishments have brought her numerous honors, including the election to the U.S. National Academy of Science and also the National Academy of Medicine and also the U.S. American Academy of Arts and Sciences. So without further ado, let us welcome Professor Jason to the podium to share with us the challenges and joy she encountered in her path to success. Professor Jason, please.
Well, thank you. It's such a pleasure to be here and to be speaking in front of all of you who are so interested in science that you would come out this afternoon to hear all of us. I have to say before I start, I'm extremely jealous of the previous two speakers because when I was in high school myself, I would have loved to have been an astronomer. I would have loved to have been a mathematician. But I am very pleased to be a biologist, and I think also my field is a really exciting one, and I hope many of you are inspired to consider it for your career. So in my introduction here with these slides, it's just to give you a little bit of an overview of the sorts of things we think about and an overview of kind of my career interests. And the overarching goal to some extent has been to modify the genome, so to modify our DNA. And why would you want to do this? Well, the older way of studying genetics involved finding some kind of phenotype characteristics of cells or characteristics of mice. And then once the DNA was sequenced, to understand what the genes were involved in doing this. But once the genomes of organisms were sequenced, especially of the human genome and, of course, a mouse genome, which offers a good model, we could ask, without knowing beforehand, what the gene is doing, what effect it has on the cell or the organism by mutating it directly. So the earlier versions were called forward genetics, but now it's reverse genetics in terms of modifying a genome. And not only is this important for biology, but it's also important in considering how to approach some human diseases. And this is a little girl where some T-cell modification took her from near death to being a healthy little infant again. So the problem, though, when I started actually my graduate work, but continued into my independent career, was how can you modify the genome? What is the approach to take in order to be able to do this? And the hypothesis was that the best way to do this would be to break the genome at the location that you're interested in studying, in the gene that you're interested in studying, or the gene that you want to correct, and let the cell repair this DNA damage in the form of a break. And it's particularly breaking both strands of the DNA helix, so it's called the double-strand break. So the problem, though, is, okay, this is a small portion of the genome, but our genome has 3 billion base pairs. So how do you break one particular spot in the genome so that you would modify just that part of the genome and no place else? So that was a particular question, and we could actually solve it by using a nuclease, so a protein from yeast, budding yeast. And this was because this nuclease, which would cleave DNA, recognizes an 18 base pair recognition sequence in DNA. So if you consider that there are 4 bases and that the chance of having an 18 base pair site is 4 to the 18, it's actually, that's 20 times more than the genome size, so much more than 3 billion base pairs. So that's the order of magnitude that would be required then for having a nuclease be very specific to cleave just one spot in the genome. And luckily, this lab at the Pasteur Institute in Paris had figured out this very problem. And so we were able to adapt this nuclease for expression in mammalian cells to address whether we could get a break in the genome or not. And again, this is a nuclease from yeast. SCE is for Saccharomyces cerevisiae. So we're putting a yeast enzyme into mammalian cells. And in fact, so this is how we did it. We expressed this endonuclease so that it would cleave in a particular region in the genome. And then we introduced a very similar sequence that would bring in, actually correct the mutant form of the gene in the chromosome. And this is called homologous recombination because the sequences are very similar, and this could correct the mutation, or at least we hoped it would. And I wouldn't be standing here if it didn't. This worked extremely well. We could see that in the absence of having a break in the genome, this event never was found. But once we put a break in the genome at this very spot, we got very efficient gene correction. The other side of things was we could get a break in the genome, and the cell, instead of using this homologous fragment, would just bring the two ends of the DNA together. And surprisingly, this also has a pretty profound usage in that it creates mutations in genes. So as I mentioned in the first couple slides, there are times when you would want to correct mutations, for example, in the case of patients that have mutations. The other option is to create mutations as a biologist studying the function of genes. So if you create a mutation, then you have a defective gene, and you can ask then what the consequences are on the cell or the organism. So we did this with this endonuclease called ISCU1, but as I'm sure many of you know, the current most popular way of doing this is with this newer class of enzymes from the CRISPR systems. By itself, an extremely interesting system because it's from a system of bacterial adaptive immunity. So just the chance finding that bacteria have a rudimentary immune system, and this involves breaking the genome. And what makes this so powerful is that it does so using an RNA molecule that can bind to DNA, and it binds through what we term Watson-Crick base pairing, so that you can just put in whatever sequence of DNA, a sequence of RNA that you want to bind to a particular sequence of DNA, and then this nuclease will cleave at that spot. So, so now we have a way of very easily putting breaks anywhere in the genome that we're interested in. And this is not only actually the human genome or the mouse genome, but any kind of organism where you can introduce this nuclease, we can now study. So in the past, we had a very limited set of organisms that are considered model organisms in biology, flies, worms, bacteria, but now it's any organism that you're interested in and can get this kind of nuclease in, you can study gene function. So it's completely revolutionized the ability to study gene function in a lot of biological systems. So an extremely interesting and powerful advance in biology. So what are some of the particularly interesting mutants that have been made? Well, we study mostly mammalian cells and mice and human cells, especially genes that are important in DNA repair and repairing double-strand breaks in the genome. Other scientists have gotten particularly creative, so putting this CRISPR system into ants, For example, to look at the social behavior of ants and finding that mutating this particular gene makes the ants no longer able to follow pheromone trails of their compatriots. And so they don't join other ants, and they have a lower survival advantage. So ants are ubiquitous, and now we can study this very particular social behavior they have using this approach. Another lab has looked at butterflies and the particular vision that they have in looking at colors. And they've also been able to do experiments to understand this behavior in butterflies to recognize different colors. So, of course, being at a medical center, it's hard not to really focus on what we hope will be a particularly important outcome of these kinds of studies, which will be to approach a variety of human diseases. This is not a gene editing paper, but rather pointing out one of the earliest genetic diseases that we knew the cause of from 1949 with Linus Pauling, so sickle cell anemia from mutations in the globin gene, a fairly widespread genetic disease, and an area of active investigation to gene therapists. So there are numerous genetic diseases that people hope to treat, and this is just one of them. But for my own case, we continue to study mechanisms of, this should be homologous recombination, and it's because it's an important DNA repair mechanism, but it's the consequences of homologous recombination are really profound on the organismal level. Homologous recombination genes are tumor suppressors. People that have defective genes, especially women, are susceptible to breast and ovarian cancer, and men to prostate cancer at a lesser frequency. We know that these genes are also critical for embryonic development. So mice that are defective in homologous recombination don't survive. And children that have some recombination, but lower levels of it, will have congenital disorders. So microcephaly, so smaller brains, limb disorders, maybe cancer predisposition. So it's important for human health, for cancer suppression, for embryonic development, and it's also responsible for reproduction. So we would never exist here, any of us in this room, without homologous recombination to make sperm and eggs for reproduction. So it's been a tremendous time in my career. I've enjoyed all of this immensely, and we try and touch on these numerous areas. But of course, the field overall is just enormous now. Once these tools became widely available, there are thousands of labs working on CRISPR and from all different angles for their studies in life science and in medicine. So I'm really pleased to have this been awarded the Shaw Prize because it emphasizes the broad applications of our studies. So thank you very much, and I look forward to discussing further with you.
Thank you very much, Professor Jason, and please take a seat here on the stage. The question and answer session is about to begin, and may I also invite Professor Chan to join the discussion.
Okay, so any question from the audience? I can't see anything. Yes, over there.
Thank you very much for coming, and congrats on your award.
I'm Ronnie from Hong Kong University of Science and Technology, and I have 2 questions for you. Well, the first one is, what's one thing that requires the most patience in your research? And the second question is, how can your research apply to people with Alzheimer's disease or people in the aging population?
So maybe I'll address the second question first. I'm not so sure we have right now any particular application to Alzheimer's disease. It would be really an amazing breakthrough if we could somehow address that really serious problem as people survive many other health crises, and then they're aging into this disease. I worry about myself or my family members if we'll end up with that kind of severe condition. But I think one issue is we don't know enough yet about the molecular mechanisms of Alzheimer's. But I have to say, any disease that involves the brain is often a very difficult disease to consider attacking through gene therapy and gene editing. Being able to modify every brain cell or a significant fraction of brain cells it is a very daunting task. And one issue, I think, with Alzheimer's is by the time it's diagnosed, there's already been a lot of damage. So it would be an area that I would love to have an impact on, but it's an extreme challenge. I think your earlier question had to do with the time frame, and maybe you could restate it a bit. How do I deal with the time frame between scientific achievements? Is that close enough? Well, actually, it's a really interesting question for me because my graduate work was working with E. coli. And so every single day, in the morning I could do an experiment and have a result. In the afternoon I could do an experiment and have a result. And so things just happened. Now, I made the very conscious decision to move from E. coli to mammalian cells, but it's, orders of magnitude longer to get results. And I just figured I needed to have the patience and hopefully juggling enough experiments to wait out the mammalian cells to grow or the mice to develop. But the reward is there because you're so much closer to considering aspects of human health or these complex biological phenotypes that you would be interested in seeing. Yes.
I'm a secondary student from Manson College. My name is Ignatius, and I have 2 questions to ask. The first one is quite stupid, I would say, because I've heard about something called zinc finger nuclease, which is, I heard that is another kind of thing that can work at gene editing. And
what kind of nuclease?
Zinc finger nuclease.
Oh, zinc finger nuclease,
yeah.
Yes.
And the first question is, the one you just mentioned, the ISCEI.
So that's a
yes.
mega nuclease, we call it.
That's compared to 2 nucleases. Which one is better? And the reason why you use that you mentioned.
Well, none of these other tools existed when I was first doing this work in the 90s. So there was no identification of CRISPR. There was no zinc finger nuclease, actually, although that was the first platform that came about. I took out a slide, but one of the beautiful things from different areas of biology coming together is that there was a progression. So we were using this an enzyme that had just been characterized from yeast, ISE1, from a yeast group, and with this 18-base parasite. Other labs decided to move to kind of a more programmable nuclease platform. So the structure that I showed of ISC1 on DNA, you could see how complex the interactions were between the protein and the DNA. So to change that enzyme with an 18 base pair site to recognize another completely different DNA site would be extremely complicated. So the movement in the technology was to find protein domains that were modular. So you could recognize a small number of base pairs using a particular domain. And so that's what evolved with zinc finger nucleases. So that each zinc finger would, 3 amino acids in it would recognize about 3 bases. And so for about 10 years, the idea was that that company or other people would develop 64 zinc fingers that would recognize each triplet, and then you just put these zinc fingers together, fused to a nuclease domain. And so that would give you the range to go anywhere in the genome. But the problem with that was, so it took a whole company of really smart protein engineers to get that to work with any kind of efficiency. But they did get it to work, but the problem was the fact that the interaction between individual zinc fingers made it difficult to predict how well those nucleases would work. So the beauty, and in between time, there were talents where there was no interaction then between the individual modules, and it was more of a 1 base to 1 amino acid code. So that was really almost a perfect system for gene editing. And so I thought when that was discovered around 2007, we were going to be in a brand new era for the next however many years using these nucleases. But then within a couple years, CRISPR came along, and the beauty of that is actually what I wrote about in 1996, after we did our experiments, that having, instead of a protein-based nuclease, DNA recognition, having a Watson-Crick base pairing gives you much more power. And so all you need to do now in the CRISPR system is you keep the same protein component but modify the RNA component. And so you can call up your company and later that day or the next day have your new RNA to do an experiment. So it's extremely powerful, and powerful not only from how quick that is, but you can develop whole libraries of to knock out every gene in the genome to do genetic screens. So if you want to ask, for example, some gene mutation causes a cell to die, how do you make that cell live again, for example, to form a tumor? And so you can do screens where you mutate every single gene in the genome and ask what allows that originally dead cell to be viable. And that's something that can only come about with these short RNA sequences that are introduced, as opposed to using much more complex protein DNA recognition domains.
Thank you. And my second question is that I believe that all of you here have heard about the Chinese scientists last year who do the CRISPR thing on an embryo to ease the problem of AIDS, if I don't remember that wrong. And I want to ask if you think that it is a good idea to use CRISPRs to modify the genes of humans to prevent some currently incurable diseases, or it is a terrible idea that will lead to the human extinction. Thank you.
Okay. I expected that to be question number one, so I was not too far off for it being question number two. But I was actually here at the Human Genome Editing Summit last November, so I was at Hong Kong University where this occurred, and I found out on Monday morning from a journalist in the United States who was asking me what I thought about J.K. Hu's experiment, and I hadn't heard about it until that very moment, and the gene editing summit started the next day, and he and I were going to be in the same session speaking, and so it was this extreme turmoil, because I had also been at the first gene editing summit, which brought in people from the Chinese Academy of Sciences, the Royal Society in London, the U.S. National Academies, and so there had been an enormous amount of discussion already about kind of preempting or considering in advance whether or not this should be done. And of course, at the time, the feeling was we certainly technologically we're not ready to do any of these things, but also we needed to have many more discussions involving many people, ethicists to discuss the ethics of the situation, physicians, and families that had these genetic diseases within them. And so here, out of the blue, comes this, we consider him a rogue scientist who's not even a physician, a physicist, as it turns out by training, who presented this experiment, really. It was an experiment. And not only on a gene that, doing this experiment without kind of approval or the understanding that this was ethical to do, but doing it on a gene that was not at all essential to mutate it in these children. So there are, of course, ways of preventing HIV infection or treating it once it happens. So if you were going to do gene editing in a human embryo, the discussion was that this would be perhaps something you would move forward to in a disease where a child would die or be severely handicapped, or clearly develop some debilitating disease. So something where a child would be born that would be severely impacted, not something that would perhaps be used to prevent a disease that the child would never have experience. So it raised a whole, of course, as you know, if you read the newspapers here or around the world, a lot of discussion and in many cases disgust from people. So I was completely on board with the scientific community and many Chinese scientists, of course, expressed their concern about this as well. That this one scientist had decided on his own, basically, to do this experiment on these children. And of course, it was an experiment. It wasn't necessary for those girls. And in the question session afterward, there were a ton of scientific questions, and my question, just as a human being, is there wasn't even any concern for that particular family. If the father wanted an HIV-resistant child, well, what he got out of it was perhaps an HIV-resistant child and another child who's not HIV-resistant. So even in the family dynamics, because there was no understanding or no discussion of how you consider ethics in a situation like that and emotional development of children, is that father going to treat both girls equally or not? And these are girls? What if they were boys? What if it was a boy that had a knockout of the gene, so he would be HIV resistant? So would there have been pressure to collect a sperm and make numerous individuals that would now carry this mutation and really change some population dynamics? So so my personal belief was that was a hugely irresponsible act by that particular scientist. But you could still consider, well, what about those original cases that we were talking about, cases where a child has a hereditary, or an embryo will have a hereditary disease that you need to correct to have a healthy child? Well, again, how often is that necessary? If you're going to go through that route of changing an embryo, why not do pre-implantation genetic diagnosis and find the embryos and that would be viable, that wouldn't have the genetic disease? This is something that already happens in the clinic, so there's a lot of precedence for it. So it kind of more and more narrows the cases where you might think that this is appropriate for saving or at least greatly benefiting a child. There still may be cases where you might ethically think this is the route to go. I have a feeling this technology is going to be applied because it can be applied, and there will be instances where families with genetic diseases do want to apply it, and it may be hard to turn back the clock and say, no, we're not gonna do it. So if there's enough of a rationale, it may move forward. However, this is still not the time. I showed you on my slide, you can do homologous recombination, you can do non-homologous end joining. The non-homologous end joining leads to lots of different kinds of mutations, but you can also have chromosomal translocations and deletions of whole chromosome arms. And when you do that in a human embryo, you have 1 cell, 2 cells, 4 cells. You can pluck out a cell to see what exactly happened, but then you're working with a single cell. So what's your chance of very accurately describing what's happening in that embryo? And if the change occurred at the 2-cell stage, if you just pluck out 1 cell from a 4-cell embryo or 8-cell embryo, you may not know what's going on in those other 7 cells or so. So how do you know that you've done the experiment well enough to make it not an experiment but a sure thing to correct a disease? So it's a really difficult problem, I think, on a technological level, besides the ethical concerns.
Thank you. Thank you. Oh, any other question from the audience right now? Yes, that's right in the middle.
Professor, congratulate you reward the Shaw Prize this year.
Thank you.
And I'm a physics undergrad, but I'm not going to do those kind of nonsense. But I have a question that last year that Dr. Thomas Reed from National Cancer Institute in the US came to CTU talk about the model that he think about the cancer cell development. And I asked him the question, which is basically based on the simple equilibrium chemistry, because all the DNAs are basically weak acid and base. So my question is how does the environment affect this kind of like DNA mutation and processings and develop to different kind of properties that we see in like medicine and biologies? Yes.
Well, we certainly have known for a long time that the environment influences DNA a lot. The surprising thing, I think, is we don't really understand that in very much detail to know in the common environmental situations that we face. how much of an impact that has. Obviously, if there's Chernobyl and you have this kind of high exposure to ionizing radiation, we know what that's going to do. But we're constantly exposed to all kinds of DNA damaging agents. What are they doing exactly? You know, there's formaldehyde in carpets, and there are things perhaps in the foods we eat, a very large number of unnatural things that humans are now exposed to. But you know, to some extent we don't know because it's hard to quantify things very precisely and to know what kind of impact that will have. But I think that's one area that's to some extent under explored, and we do need to know better the agents that we're exposed to and how much that's doing to DNA. Now, on the flip side of things, it's interesting to consider. So every cell, you know, from the time you're going from a one-cell embryo to a two-cell embryo, you've probably already underwent a mutation or two, and that is going to continue. So probably almost every cell in our body is going to be slightly different in the 3 billion base pairs from its neighboring cell. And we can know this even more dramatically. So actually, if you want to, if you look at tumor cell, well, if you look at cells from young people versus old people, there's almost like a clock, a mutational clock, where you could gauge how old an individual is by the number of mutations that they've accumulated. But on the flip side of things, studies have been done where what seems like normal tissue, like from an eyelid or an esophagus, have been sequenced, and there are mutations in cancer driver mutations, but there's no cancer, and there will never be a cancer, almost certainly in that eyelid. So obviously there are lots of mutations that are in the genome, and there are lots of mutations even in cancer driver mutations. So what prevents those cells from, you know, our skin often, you know, in the exposure to UV sunlight? We have lots of mutations. P53, if you're familiar with, people can look at that and say, oh, you know, by sitting out in the sun for 1 hour, you've accumulated 1,000 more P53 mutations in your skin, but you're not necessarily going to get skin cancer. So there's really a lot we don't understand, and so there's lots of room for young scientists with energy and creativity to address these areas.
I have quite a number of questions on hand, so maybe I'll ask you then. So for someone who was scared of biology, by the enormous volume of information to learn, how could they get into it properly?
Well, you know, the traditional ways of teaching biology have always involved a lot of memorization, you know, categorization of organisms or, you know, parts of the body or things like that. And, you know, it's helpful to have some of this information on hand. But actually in my undergraduate biology courses, I memorized all those things, but they didn't really turn me on. What turned me on was molecular biology, so something that it wasn't just memorization. You could understand things, processes like mutations or you know, cancer development or whatever. And the other point is that molecular biology is a highly quantitative scientist, so you can design experiments where you can measure things and therefore with fairly good certainty draw conclusions, and so you don't have to get stuck in this memorization of a lot of facts. You know, it's much better to move beyond that into something that's more creative. And then it's a lot of fun if you think about how you can design experiments to address certain questions, like the one that we just discussed.
Yeah, agree. So next question. When did you develop interest and competence to become a Greek scientist? Who might have helped or inspired you?
There wasn't really anybody in particular, like often people say, oh, I had a great teacher, but there wasn't, I would say our like when I was a school girl, there weren't, I didn't think the science in school was very interesting, partly because it was this memorization sort of thing. But I was able to get some books on my own to study various things. Like I tried to teach myself the theory, the equation for special relativity, and so what could I learn on my own? But I have to say, what was really fun growing up was the space program. So we already heard about Sputnik, and that was a little before my time. But when I was a child, on the television, and everybody watched 3 stations and 3 networks in the United States, and if there was a space launch, that was shown live on national TV. We grew up in Florida, so actually the launches were fairly close to where we lived, and I went a couple times. And so science was front and center for as children growing up through the space program. And I'm kind of sorry that, at least in the US, children don't have that kind of exposure to science. Is a really exciting field to think about. And in fact, such large areas of the country are sort of anti-science. So that's particularly disappointing to me. But things like evolution that we learned about, but the space program having that front and center really made me consider science as a future career.
I believe so, but I think that's probably people outside the U.S. may not understand that, though. Yeah, I agree with you what you said. So another question: do you have any advice for young prospective biomedical scientists? How can we know that if we are suitable to become a researcher or scientist?
Well, I think this was mentioned maybe by Michelle. You have to have a real passion for science. If the area of science you're going into, if you're not excited by it, then you're not going to be successful at it. You just can't do it as sort of a side thing that you do a couple hours a day and feel like you're going to accomplish something. You have to have that passion that's going to bring you in as you do these experiments that may not work, or you have to repeat over and over to have certainty about things. So it's really important to have this passion. And I think it's also important to have some degree of creativity, so you can innovate, you can ask new questions. But if you don't have a passion for science, you shouldn't do it, because it can be difficult at times.
Yes, good. Okay, another question. This is quite interesting. So the biological sciences is a rapidly developing and very popular field. So where many researchers are being trained every year. Have you ever had the experience when the idea you had was already researched, and whether being the person to produce revolutionary research in life science is difficult?
Because there are constantly new discoveries, I think it is an expanding field. But certainly, there are many questions that can be addressed where people will come to those same questions, and so then there's competition. So I know when we did our experiment in '94 that other labs were interested in doing it, but maybe didn't have the tools or capability. But there was another lab that designed the experiment slightly different, and they published the next year. So we were lucky in being able to do the work first and before some other lab. And then because we had developed these tools, we could move on in this cancer gene situation with the BRCA1 gene to show that it was critical for homologous recombination. And so we could, again, do that before other labs. But then the approach was out there, and then 2 years later, we published BRCA2 is critical for homologous recombination, but then 2 other labs later that year published that as well. So you could see things kind of ramping up. And now the field of homologous recombination involves hundreds of labs. So there are luckily still lots of questions, but I think this is one thing, one very important correct decision that I made in moving to my own lab, which was to find an area that people actually did not care very much about, like Michelle said. So at the start of when I did the experiments, there were very few labs that cared at all about it. And so it was a really unexplored area. So there were like 5 years where we could work not alone, but a very small number of labs doing recombination in mammalian cells. So we could really make an impact. We didn't come into the idea of doing something that would form some niche in a much larger field, but hope to expand, that the field would instead expand and we would open up something new. So that's certainly one advice to any young scientist I would have. Don't do something that everybody else is doing and maybe asking one little question off to the side, but try and have a broader vision of what would be important.
I think this is great advice. I think for anyone who's going to do science, I think that's the advice they should take seriously. Okay, let's see. The other one is that do you think in modern science, being a scientist with more than one focus has more advantage than is it getting more important to focus on one single area?
I'm kind of a couple minds there. So as I mentioned, when we started, there weren't very many other labs doing things. And so I started doing some work on basic recombination mechanisms on these tumor suppressors and on reproduction because these were all natural areas to go into from our original observations. We, in that experiment designed for gene editing purposes, we learned a lot about what the cell does naturally. It does homologous recombination at a high efficiency, and we could figure out, we could address all these areas in tumor suppression, reproduction, and even embryonic development to some extent. So my lab has continued to go along these 3 areas, and so to some extent now it's a little bit unfocused because there are whole labs that only study not only BRCA1 and 2, but just BRCA1 and maybe one aspect of BRCA1, and other labs that study double-strand break repair during reproduction, and they're only studying testis, sperm development, and in mice, and that's the sole thing they do. So they're highly focused. So we do these areas, and so these 3 areas, and so in a way we're rather broad. But I think that it helps to have a little bit, maybe again, related to something Michelle said. If you're thinking about something different and then come back to some original problem, I mean, they're not so different, that maybe you can have a little more insight into the other problems because your mind is moving in a little bit of a different direction.
So any question from the audience?
So good afternoon, Professor. So good afternoon, professors. And I am a student from Diocesan Girls. I am a physics elective student. And I have a couple of questions regarding genetically edited food and organic food, and also about plastic surgery and vaccines. So for the first question, so there has been this sort of rise in people fighting for organic food in the midst of people doing more genetic editing stuff, including in agriculture. So do you think genetically edited food is better than organic food, and does it impose a threat to human bodies?
Well, certainly genetically engineered food can be organically grown, so there's not a necessity to have that distinction. Of course, we all like things that are more natural, and especially in the European countries, there's a prohibition in many cases about using genetically engineered food. On the other hand, I think that that can be quite naive to say we're never going to use genetically engineered food, because so much of the world has food needs, and to develop crops that may be resistant, especially now with climate change, maybe resistant to drought or resistant to some pests, that may be the only way to solve some of these food needs. So I'm not a agriculturist myself, so I can't really comment on various things, but to me, it's not such a leap forward to think we can't have genetically engineered food, because we, of course, we genetically engineer food all the time by doing breeding experiments. It's just that takes a long time. So if you can take something that we know in one crop prevents a pest infection and put it into another crop by making a single base pair change or something like that, why would that be so bad? It can save a lot of breeding time, and it would be something you could do naturally, and people have done for hundreds of years in terms of breeding. So again, I can't really speak about the state of the field overall, or even some particular crops with any kind of particular knowledge. But just as an outsider, to me, it doesn't seem like genetic engineering of crops can be so bad. Now, of course, there are other issues, like if some crop in Africa needs constantly some new seeds from a engineered company, is that ethical or not? That sort of thing. If you're going to engineer something that may affect the larger environment, of course, that's something we need to watch out for. So I think there have to be some controls on things, obviously, but I think the particular logic of engineering crops is not such a bad thing. And in fact, I think we're all likely to have, gene editing is likely to have a more broader impact around the world in agriculture than even in medicine, because large swaths of populations will be affected and be able to make use of this technology.
Okay, thank you so much. And for my second question is, a lot of people in this world also strive for beauty, and at least they have to meet some sort of standard. So what are your opinions for people thinking of doing some sort of genetically editing in order to make themselves more prettier, or to reach some sort of beauty standards in the world?
Even in the case that was brought up with the CCR5 editing to prevent AIDS, so some people have called that an enhancement, and it's more of a prevention of a disease, but it started to raise the same sort of issues, for those girls, if we consider, well, if that was an enhancement to make one girl more beautiful, it just seems ridiculous to me. I mean, we have global warming on our, and destructions of whole ecosystems and loss of species around the world, and for anybody to be concerned about looking a little more beautiful just seems absolutely ridiculous to me. So I'm sorry if that concerns you, but it doesn't really concern
it doesn't.
me.
I'm just asking for like some students of mine who couldn't come because they have
I didn't mean to
activities
make
at
you
school.
defensive, but
Okay, so because of time, I do like to ask a question before we end. Now, because in fact it's related to the question that the lady asked, and also related to the second question about using genome editing to correct for genetic errors. The question is, how precise or how accurate is genome editing itself? I mean, how many, like for example, like off-target editing will happen?
Well,
do we know?
Yeah, I think people are getting better and better about preventing off-target things. And actually, we do genome editing all the time in our biological studies. So off-targets are not the most horrible thing. As I mentioned, there can be other mutations. But, the main point is we're getting better and better. But on the other hand, I think the on-target thing is still the bigger issue, depending on what you do. Now, if you're doing something in somatic cells,
that's different though,
where you can sequence the cells and know exactly what the base pair changes are, or that there are no other base pair changes, that's fine. But in the case of embryos, where you have so limited material, and we wrote a commentary for a paper that was published in Nature about a cardiomyopathy gene, and the authors had postulated that the DNA repair was going one way, but they had no evidence that it wasn't because they've lost a whole chromosome arm or something much more drastic. And I think it wasn't a trivial thing for them to look at because they're looking at one cell from an embryo or a couple cells from an embryo. And so I think it may be that those kinds of on-target modifications or on-target locus cutting is more of a problem because you can't always investigate things well enough to be able to rule out that you didn't have a more dramatic event.
Well, with that, let's thank Professor Jason for a very informative and intense talk. I think we also should thank all three laureates this afternoon for giving very inspiring and interesting talks to us. So thank all three laureates.